and collaborator Wang. Let me see here. So he's a collaborator of this paper for this talk. So we worked overnight last night for the slides, and I think it's ready now. It's good. So I hope it will be smooth talk. So the talk is about spatial segregation in reaction diffusion epidemic models. It sounds pretty general for the modeling part. And the focus initiated was on this segregation, but of course we have some mathematics for the comparison and also derivations from some simple so-called cognitive movement of diffusion operator. And it's a joint work with a PhD student, Wang, and Professor Yoon-Jun Kim in Korea. Okay, I cannot move it. Oh, stuck. It was moving, but no. Yeah, cannot move.
Page down, page up, cannot work.
Oh.
What about now?
Yeah, it's good. Okay, thanks. Okay, it's working. So mainly, I hope you can get some take-home messages about two things. One thing is about some kind of cognitive diffusion operators. Very simple version here. It's almost a silly version, but it's a good start, I think, for the so-called smart people. So we move not randomly, not like chemicals. So similar idea from animal movement we take from our review paper. And the other message is about the segregation, whether segregation can occur. So here segregation, I try to call it the natural spatial segregation. Because normally I call it segregation, you may feel we give some isolation policy, isolate people, then of course you have segregation. That's interesting, you have that, right? Everyone isolated, then you have this segregation. Natural segregation, I try to say, we just behave normally as a human. Can we get some kind of segregation? And next question is, if you have segregation, can you get, can you control the disease? Or maybe yes, maybe not, right? So try to explore those questions in some simple way. Okay, so some outline about this talk. So with motivations, I will introduce a group of reaction diffusion models using the simplest SIR type. Of course, you can extend it to SI. This is SIS type. Right? You can extend it to SIR or SEIR or other types. And with some mathematical results. I picked some results here to put in because of the time limitation and with illustrations. Then last part, I will talk about segregation and also the outcome. Outcome is, can we control the disease without any policy given, kind of. So conclusion, because a lot of disease is actually controlled by itself, even you don't give any isolation or any intervention, right? So motivation, you can randomly pick this example. Just show you have spatial heterogeneity in distribution of hospitals, the distribution of a lot of stuff that will affect the transmission, for example. Right? So that's natural. You can pick any example you want. So that leads to the existing work, right? I think this work like a lot of follow-up work now, right? So this was developed by Linda Allen, Ben Boker, Yuan Lo, and Andrew Navy. I think most of you probably know this one. So they have a few papers relevant to this, also discrete space version. Okay, so what's new here in their model? Just beta of x, r of x. Right? So you have spatial heterogeneity in the transmission and in the recovery. Right? And of course, you expect something interesting compared to the constant coefficients before. Right? And a lot of work, follow-up work, including Professor Xiaoqian Zhao's work with Zhongrui here. So I don't go deep into those stuff, just show one important one, as in Xiaoqian's talk, Arnold. Right? So when we talk about epidemic model, talk about Arnold. So they have obtained this variational expression for Arnold. So we'll see similar stuff, okay, from slightly different diffusion operators. So what this can give us, asymptotic behavior and monotonicity of ANO versus DI, which has a big question, right, for this correctness. Okay, so we have similar issue, of course, if you change the operator, but that's not the goal of this work. And the existence, stability of disease-free equilibrium and asymptotic dynamics or behavior of endemic equilibrium. That's the threshold behavior of given by ANO, right? So that's pretty standard. Now let me introduce the first important part about the derivation. So here I try to use the simplest way to derive it. So there are more complicated way in our review paper or in Mark Lewis' paper. I will show you soon. So this way here is kind of a bit like simple, but I think easy to understand, but not general enough. A lot of cases maybe not included. So we look at some special cases. So in previous model I showed you from the Linda Allen's and collaborators, beta of x, alpha of x, right? Spatial heterogeneity in those coefficients, but not in diffusion, right? Not in diffusion. So the constant diffusion term from Brownian motion, of course, we are not that stupid, right? Nobody move like chemicals, right? So we need some improvements, even though the next step a bit better, but still not the reality. But I think much better than the random Brownian motion, right? We are not chemical. So humans obviously have very strong cognition, very strong, even stronger, much stronger than animals. The simplest cognition is something like chemotaxis, like bacteria. They are not that smart, but still they have some kind of selection for direction. So that's we have very detailed expansion of this perception, memory, and learning in our review paper here. So we just put that in the PDE setting, PDE modeling, how we model this perception, how to model memory, how to model learning one by one. Okay, one by one, we discuss there. It's not like we solve it, no. We summarize what we have and propose possible modeling ways for future. So it's not resolved, but just try to give some ideas for future modeling of this very complicated idea, kind of. Of course, we are just Yuri gave a talk yesterday, right? So mathematically, it's very challenging. So we have very limited thing to do. Like transient dynamics, the same. Very important, but we're lack of mathematical tools. So to model this, we consider this very simple patch model, right? One-dimensional space, kind of, right? Can extend it. And we have this master equation, right? So this Cij is more like the rate, right? For the migration, kind of from one patch to the other, right? So you have different possibilities. And you just the kind of population or density, right? So you can see the master equation. Okay, I don't expand this, but it's very simple. Right? We give this in math bio course, right? Just write down term by term, right? So what we are doing, ui dot, so the change of ui, right? This guy here, and how this guy can change. 1, 2, 3, 4 arrows, just write down, right? So get this master equation. So first case, so we have some spatial cases. First case, symmetric. What's the symmetric mean? We have this Ci I plus 1 equals Ci plus 1i. Okay, what's the other one? These two guys are the same, right? That's called symmetric. Of course, same for these two guys. Right? So that's called symmetric. So I move from here to here or move from here to here, same rate, right? I can say same probability. Okay, so from this, we can use very simple calculus to get this form. Right? So it's a very simple approximation. So ui dot will be this. Of course, we assume because they are the same, we just give some notation. If you don't like plus half, doesn't matter. Just some value in between. You can put something else. Okay, arc psi, for example. Then we can get this, right? Simplified version. Then we can get this, right? This is kind of very simple mean value theorem, right? From calculus. It's very simple. Then these two use kind of approximation for the derivative, right? The definition. So we get this form. So we can get this kind of from fixed law, right? From fixed law in physics, we get this. Here, of course, we use this patch to derive. Right? So this one follows a fixed diffusion law, right? So Fickin diffusion equation. Or we can call it later. I just call it the symmetric case or symmetric diffusion. And there's some reference here, right? Okay, relevant. So Kim's paper and also Professor Sam Levin's book, right, had in old days they already had some kind of some summarize about this. Okay, summary about this. And I think that one is popular, right? I saw when you have spatial heterogeneity, many more papers use this one compared to next one. This one is more popular, but then I mean this one is more correct than the next one. No, in most cases, I think the next one is more correct. Of course, both can be wrong, but this one, I think in many cases can be more correct. Okay, so the other case is Ci minus 1i equals Ci plus 1i. So this just means from I patch to I minus 1 patch, right? Move to the left. And from I patch to I plus 1 patch, so the move to the right. So you can see more clearly from that graph. So that means from here to left, from here to right, same probability, right? Same probability. So I move from here to left, or move from this spot to the right, same probability. So that's, we just call it random movement or random dispersal, right? So that can give us something different. So we give a name, okay, they are same from here to the left or to the right, same rate. So we give name gamma I, right? And similarly, we can get the approximation for second derivative. So that one will give us the, so just simple calculus, right? So we can get this Laplacian operator outside with this some kind of spatial heterogeneous function, right? Times u. Now, of course, we see that many papers have no derivation. Just say, I like this one, I like that one. But there's some kind of interesting background there, right? And this kind of the simplest version we can have, I think, this kind of derivation. Not general enough, again. So we'll see something different, but these are special cases. And also the cognition here compared to our review paper, if you have time, you can read our review paper. Much more complicated than this case. Okay, this one just kind of silly case, but I think it's good to start in order to do some mathematics. And this paper, this Mark Lewis and his student and postdoc paper has more general derivation, but very kind of, I think, much harder, okay, to understand. So if you have interest, you can also read that for the derivation. And in their case, not just get this one. So they will get more general case with power there, right? So these two guys are special cases. I can show that one, their derivation, but it will take much longer time. The version I show here is kind of much simpler version. I think any student can understand. And if we have random and symmetric, what do we get? Then we get the homogeneous case, right? So if all those rates are the same, then we just have this spatially homogeneous diffusion. So like the first model, right? Model 1.1. Right? So here just summarize. So we just apply this to the epidemic models, right? Before we just derive by the single species, right? So we can apply that operator to here. So that's the Laplacian operator outside, right? So that's called the Fokker-Planck type, or later we just call it random diffusion. A bit confusing, okay, a bit confusing, random diffusion, but we just mean this spatially heterogeneous random diffusion from that simple derivation. And okay, what's that? Yeah, this one, and the other one, we got this one, right? The symmetric case. So kind of from fixed law, right? We can get this form. Of course, we both derive from the same master equation, right? Under some simple assumptions. So we can put this one like this. So here we just not only have the spatial heterogeneity in parameters and also in the movement with a little bit cognition, right? Little cognition in human movement. So which means we are smart, right? We are smart. So these guys, F and G, will be connected to the severity of the disease spread, for example, or the distribution of hospital, or many factors. You can throw it in. Okay. So I will show you some examples, but it can be very general. Okay, very general. F and G can depend on many factors. If you know their distribution, you just connect them. Because our decision will be based on those things. So if I'm sick, I try to go to hospital. That's the normal way. But if you use Brownian motion, we are stupid. Okay, I'm sick. I'm very sick. I don't go anywhere. I just roaming around randomly. That's weird, right? So for healthy people, it's the same. If I know, for example, I'm in Toronto, if I know water is very severe, for example, do I go there? I don't go there because I know severe there, I don't go. So that's very simple cognition we have. So we're not that stupid, right? So we'll kind of have some kind of judgment based on situation. So we'll try to start from this so-called cognition, right? And we want to see whether that makes a difference, because that's the reality. We are not motion like particles, right? So that's the reality. So a lot to be developed on this talk, I think. And if we want to compare mathematically, what's the difference between these two operators? Because these two are most popular ones people use. When we have spatial heterogeneity, consider how that affects the diffusion. These two are most popular ones. And as I said, if you check how many papers on this one and previous one, so I think more papers, more papers on this one, I think. Fixed law, right, on this symmetry case. But which one is more reasonable? If just these two spatial cases. One is symmetric, I move from here to here and back, same probability, or move from here to left to right, same probability. I think random one is more, in many cases, more realistic, I think, more reasonable. So I would say, in many cases, okay, if we have no idea, I would say I would just use this one, okay. If I have no idea about anything, I will use this one. But most papers actually use the next one. But if you check Mark Lewis' papers, most of his papers indeed use this one, not the next one. Yeah, so I just pointed out. So I don't say which one is right. Both can be wrong, but it depends on situation. Okay. And the difference between these two operators, pretty simple, product rule. Right? Product rule. So you have second derivative here, right? You put one derivative in, right? Kind of. So just product rule, and you will get these two guys, right? These two guys from product rule. Right? So it's very simple. So just take one derivative in, right? So put gradient in and keep the divergence outside, right? So you will get these two guys. You see that it appears, okay, this one. This symmetry case appears here, right? This operator, you see, this one here, it's here. So it's kind of this random case has extra term. So we expect that will be more complicated and mathematically, right? And give something different. And indeed, that's the case. So here's the conceptual idea I plotted by hand, and the student just put into the graphic tool to make it. It's not in the paper because too kind of naive, right? Put it into paper, yeah. And but the idea is roughly here. So beta of x, r of x. So I try to put this supermarket, for example. So probably you have high transmission rate if you have cluster of people together, right? And what's the behavior of human? So if we have high beta there, maybe in the epidemic or pandemic time, we try to escape. We don't want to stay there, so we try to escape, right? And this recovery kind of, oh, I put a hospital, right? We put a hospital here. So recovery is high. If I'm sick, I try to go to the high R place. It's kind of hospital or clinics. So, and in fact, people try to stay, right? Try to stay until you are fully recovered. You leave, right? So try to stay. Yeah, so the model is not for specific disease, not for COVID or anything, but just the general discussion. You can explore the general mechanism. Yeah, so now this will give us something for this kind of diffusion, right? Spatial heterogeneous diffusion, depending on something. Of course, based on this, just example, right? Based on this beta and R, right? You can have this. You can have other factors coming. Right? So why we have R to -1? You can just put the function of R here. Doesn't matter. You just say that's decreasing function. The reason I put this, we put this one because we just put the increasing functions for f and g. For example, proportional. Then we put the beta here and R to -1. We just say diffusion coefficient should be smaller if R is larger for that location, right? And if the transmission rate at location X is larger, then the diffusion coefficient of that susceptibles or healthy people should be larger, right? So try to get that in some simple way. Okay, not necessarily R to -1. Just need this guy is a decreasing function of R, that's it. So this one is an increasing function of beta from that simple cognition of human. Okay, so I will show you some mathematical results. Need some basic assumptions. So here we have some kind of cognition, right? Cognition, the model. You can also see additional papers. So this idea also relevant to this so-called starvation-driven diffusion, right? And it's I think much simpler version than our so-called cognitive movement modeling in this review paper. So these two should be not that hard, just similar idea. And this one here, if you're interested in this area, maybe this one is a good one. A lot of open problems and also future approaches suggested in this review paper. So not just a review, because we don't have so many models in this area yet. Yeah. So we have some models from Mark's group and like Paul Moorcroft at Harvard. So they have some sense, but not many, still far away from the reality. So here we have some basic assumptions. So we need this function, these diffusion functions, right? F and G should be bounded from above and below by two positive numbers. And second assumption, I think these assumptions are mild. The second one is always true, I think. So beta of x greater than r of x is non-empty. In most cases, actually, most places, this beta is much larger than r, recovery rate. So it's non-empty, just mean, well, if it's empty, not interesting, not interesting. You have no disease. Just recovery rate is everywhere larger than infection rate, then not interesting, the result, right? So we ignore that. So some theorems to compare. Sorry, I don't put the regularity, because some people may have interest on regularity, like existing uniqueness and the positivity of solutions and bounded above by something. So we have done that in the regularity theorem for these models. Because that's not scientifically interesting, so I just ignore that. And here we can also have a variational form for R null, very similar. So the claim is this model. So this is for the 2.5. So it's about the symmetric diffusion or fiction type. So for fiction type, this one very similar. The only difference is this constant before here. This is the di before. Now becomes this g of R2 negative 1. So no difference. No difference. It's the same thing. And indeed, in the simulation, I will show you this model, no difference. Even though it has spatial heterogeneity in diffusion, looks more complicated, but no difference. Whatever math or simulation, not much difference. But the other one will give quite a bit different, the other one, the random case. And this assumption is, I think it's reasonable because beta of r minus r of x changes sign in the region. So if we have hospital and supermarket, that's reasonable. So in supermarket, this one is positive. In hospital, this one is negative, kind of. All people just go there to get recovered in the hospital. And they are, most of them isolated. And we proved the following results. So R null, the monotonicity, okay, of R null with respect to E, that's similar to that constant diffusion case. And we have limiting case for this eta. So eta, I can call it magnitude of the diffusion rate of infectives. So infect people, how fast you move, kind of, that's the magnitude. And of course, the profile given by this G, this function G1, that gives the shape, So we can see that eta goes to 0, which means in fact people don't move. We have the limit for R null, right? And if move very fast, of infected people move very fast, then we have R null goes to this guy, right? And I will illustrate this numerically. We can validate kind of this because we prove it here. And we can obtain upper bound, lower bound for this R null. And the sign of 1 minus R null is the same as sign of this zeta star, which is this complicated formula. I think this idea is similar to Xiaotian's talk yesterday. Yeah. Yeah, so when we deal with this kind of thing, we always use Xiaotian's method. Yeah. And from R null, these are typical results, right? So we proved that if R null less than 1, we have global asymptotic stability of this disease-free equilibrium, and R null greater than 1, it's unstable. And we prove this uniqueness of the disease-free equilibrium, right? So the boundary one is not hard. And the harder part, of course, for this one, if R null greater than 1, and then we have at least 1 endemic equilibrium. So here we cannot prove uniqueness, but the more complicated one, next one, we can prove. So it's interesting. Simpler model, actually, we cannot prove uniqueness. We prove at least 1 endemic equilibrium there. One thing to mention here. So this disease equilibrium is kind of constant equilibrium. So see that S null tilde, it's constant, independent of space. Right? So we also see that in the simulation. And in comparison, so something new here, okay, something new here. This one is the so-called spatially heterogeneous random diffusion model or focal plug type, right? I derived those two, right, at the beginning. So this one is more complicated. In the calculation, you will see in the proof, basically just divided by each term, divided by G1, okay, divided by G1 here, G1 here. Okay, where this eta come from? So G over G1, right? So if you look at the previous one. So here we have G here. So G over G1, that's eta, right? I assume that's eta. So it's just simply each term divided by G1 in the calculation. So it's a more complicated form, right, for this Arnold. And some results are similar, but some are different. So like 1 is the same, 2 is the same, 3 is different. Okay, 3 different. Before we don't have this divided by G1 here, divided by G1 here. So in both integrands of numerator and denominator, we have divided by G1, right? Divided by G1 here as eta goes to infinity, right? In simulation, we also see that this eta goes to 0. Both models give the same limit, but when eta goes to a large number, they give different numbers. And of course, that's important information because eta just means how fast these infected people move, right? And that tells us limiting case. If movement is very small, very large, what's the result for this basic reproduction number, right? Unknown. And this one is the same. Okay, number 4 is the same. And this one also different. This one looks same, but lambda star different from this previous zeta star. So again, this one also just divided by G1, right? Divided by G1. Right? This one here, this one here. Again, this is G over G1, it's eta. So in the proof, you will see that's the calculation. So we try to see the difference mathematically, right? So sorry. Okay, so next result, again, we can show that system has unique disease-free equilibrium. What's the difference here? This one depends on space, so it's not constant equilibrium. So for this model, disease-free equilibrium depends on space, S hat of X. Right? So that's the main difference. And we can have this dichotomy, right? R0 less than 1, global asymptotic stability of this disease-free equilibrium, or R0 greater than 1, unstable. And for R0 greater than 1, we can show there is a unique, so here we can show a unique endemic equilibrium, right? So we have a unique endemic equilibrium here with whatever satisfied. Right? Now let's look at some examples. So these examples are not that interesting because just validation, illustration of the math results, right? So it's debatable, okay? Some journals say you don't need that. Some journals say, yes, you need that, okay? So it depends on whether it's more mathematical. More mathematical journals want to see something maybe to show or illustrate the mathematical results. More applied journals say, okay, I don't care. Show me scientific interesting results in simulation, right? I don't care about math result is right or wrong. I just assume that's right because you prove it, right? You prove it. Why you need to show us? That's weird, okay. So I just briefly mention that here. Yeah, we'll jump to the segregation part. So we can choose these functions, f and g, and beta and r, right, in some form. And here, no specific purpose. In the segregation part, we indeed choose them in specific purpose. We want to check some hypothesis or answer some specific question, we choose that form. Here is not. Here just show the illustrated math results, right? So no specific form designed. And one thing I want to mention is this C1, you can treat this as a control method, for example. Intervention, for example, you say if you have C1 larger, this is transmission rate is smaller, right? And it's spatially heterogeneous because when X is small, so on the location, X is small, which means on the left, this impact of C1 is less, right? And X is larger, the impact of C1 is larger. So it's just some heterogeneity there. So we can plot this R0 versus C1, right? Of course, it's decreasing, we know that because C1 decreases that beta, right, transmission rate. And we can see where we have R0 is 1. When C1 is 0.65, we have R0 is 1, which means if C1 over this number, right, 0.65, disease is controlled. Right? And R0 versus this eta is still that magnitude, or you can say how fast the infectives or patients move. Right? So again, there's this kind of paradox or what's puzzling us, right? Same as Linda Allen's paper. Right? And we can check this limit. When eta goes 0, eta goes to 10. 10 is very large. So you can choose eta goes to 100, same result. So 10 is large enough. So this, we can get eta goes to infinity, right? That's this one. So we just show that numerically, and indeed they are consistent. Right? It's kind of validation of the math result. And we can show that if R naught less than 1, solutions just tend to the disease-free equilibrium. Right? I goes to 0, S goes to a constant. That's in the theorem. That's in the theorem. So in this symmetry case, right? Symmetry case, the S goes to constant, right? When R naught less than 1. When R naught greater than 1, then we have some endemic equilibrium. Right? Solutions tend to some endemic equilibrium. So in comparison, so 2.4 is that random diffusion one, right? That Fokker-Planck type. So we can see that R naught also decreases over C1, but threshold is smaller, which means for this case, it's easier to control the disease because threshold for C1 is 0.54, which is less than previous one. So for this model, indeed, it's easier to control. If you have random movement, right? Move to left, move to right, same probability. That will make this easier to control the disease. And again, we have this R naught versus eta here, right? And we have checked this limit as eta goes to 0, eta goes to infinity, right? So validated result, and also you can compare with that previous case. So first one is the same as the previous case, as the Fikin case, right? Eta goes to 0, 1.6738, the same thing as previous one. And as eta goes to infinity, here just eta goes to 10, then the limit is smaller than previous case. Okay, that's, if you still remember in the theorem, we have divided by G1, right? Divided by G1 for those terms, so it's smaller. So this also indicates it's easier to control in this case. That's when R naught is smaller, we like that. Okay, we want R naught to be smaller as much as possible. So here we have the R naught less than 1, right? So you can see 10 to the disease-free equilibrium. From theorem, we have known I goes to 0, S goes to some function of X, not constant. So this case, we don't have constant disease-free equilibrium, right? It depends on space. And also kind of validation for the theorem 3, right? Theorem 3. Okay. So calculate this S hat and compare with the number numerically. Right? So if R naught greater than 1, we can show that this endemic equilibrium is attracting. Right? Solutions tend to that. Right? Tend to that. So okay, so that's kind of illustrating of the mathematical results. So I think running out of time. So spatial segregation. Okay, I don't read this rule. I just use this motivation from this well-known person, Thomas Schelling. It's Nobel Prize winner, I think, in 2005, right? In economic sciences. So of course, this idea is prevail everywhere, not just in biology, right? Everywhere. So if you start with this kind of pattern here with 2 markers, right? Circle and sharp, then maybe over time, right, under some mechanism, you still get something like this, not segregated. It's lucky. If you are lucky, you get this one, maybe it's segregated. So you can see that circles here and circles here, right? And sharps here. So it's kind of isolated of these 2 markers. Right? So that's a very simple idea of segregation. And that's the definition, right, from this Thomas Schelling's paper, right? So segregation is a phenomenon that population groups are separated in certain areas. Right? So straightforward definition. So now the question is whether those models can give this naturally without controlling method, right, or intervention, and whether that can cause, if we have segregation, can that help control of disease? Logically, yes, right? Logically, yes. If we have isolation, that's good. That's why we have the intervention, say isolate, lock down, everybody stay at home, right? That's the reason. Logically, yes, but actually not. I will show you, not necessarily. So, so first, I'll show you this. We define these indices, right, for segregation. So one is kappa, so kappa is larger, then segregation is stronger. But this one is important, chi here. So this chi, if it's positive, no segregation. If it's negative, then there's segregation. And which segregation is strong or weak will be determined by this kappa here. So we have combination of indices for the segregation. We don't know whether it's optimal version. Maybe we can find a better version. So like you already discussed yesterday for the measure of the fragmentation, same issue. So we try to quantify so-called segregation. Do we have segregation? And segregation is strong or weak in some way. So we hope that's better than visually see segregation or not. So first example about segregation by dispersal. So this one indeed will show you one model can give segregation. So logically we know diffusion is bad for the segregation. So if everyone just stay at the same location, that's good for segregation. If you have mixed up, right, by diffusion, then normally segregation disappears, right? So probably that's in the, let's see, okay, not here. So for comparison, we put this OD model. So it's kind of infinite dimensional OD because for each location it's OD. So that's infinite dimensional OD. We just kick out that diffusion term for comparison purpose. Okay, we're not interested in this, but for comparison purpose, if exactly no movement, what's the situation? That can give us the idea if you have movement, right? So kind of extreme case. And the other one we compare is this spatially homogeneous diffusion case, right? So it's the same as the first model, okay, of this talk, but here we point out because we want to have reasonable values for the diffusion coefficients here, ds, di, because they are constants. So we take the average of these functions f and g in the space. Right? So that's for the comparison purpose, we do that. Otherwise, you will say, oh, we may choose some too small or too large diffusion coefficients in that spatially homogeneous case, right? So we pick some functions and, okay, probably I need to skip this. So here we want to show, indeed, spatial heterogeneous random diffusion can lead to segregation, although other two diffusion models cannot. Okay, so that's the conclusion I will show you. So, okay, let's chosen beta and R, a minimum in the middle, right? And F and G will be opposite because F, it will be proportional to beta, but G is 1 over R, right? 1 over R, so we have this. So can you see we have segregation here and segregation here, right? No segregation for these two, right? So that's kind of the direct observation. And statistically, we can compare this. So say, okay, this chi is negative, we have segregation. So this OD or random diffusion will have segregation. And this will give the rank, right? Which one is stronger? And this one give us the result. So we can see the random diffusion indeed gives the smallest infection fraction. Indeed gives that. So caused by segregation, right? Caused by natural segregation, not by intervention, okay? So maybe only 1 minute. So next case, we try to show, okay, I try to show you, sorry. This is a case, seems like we have segregation. Sorry, it's not modified. What's this one? Second one, yes, here. So we can see this one will have this so-called disease-free region in the OD case. And this one, we can see no segregation. So this diffusion model have no segregation. OD, of course, have, but diffusion models don't have segregation. But this I is still very small at the state level. So it's still very small. So it's controlled, even though no segregation, right? No segregation. So that's the conclusion here. Even no segregation is not necessary condition to control disease, right? Because you have other ways, right? So the mechanism is here. Okay, what's the reason? Because the random diffusion takes advantage of disease-free region in OD case. That's the region X greater than 0.5, right? Where we also have high recovery rate. So you have other mechanisms to control the disease, not just the isolation of people. And sorry, this case, this is a modified case. Okay, what's the point I want to show you? I just tell you the result. Okay, no time. The paper is already online, so you can check the paper. So the conclusion is the disease-free region is a necessary condition for favorable random diffusion. Modified case here I want to show you is without that disease-free region, it's impossible. No segregation, then no disease control. Okay, because previous case is kind of extreme case. We have a disease-free region. Not necessarily we have that, right? we may not have that. Yeah, so that's extreme case. And last example, just dispersal toward endemic region, that will make the random diffusion case worst. That will give the worst scenario. Okay. And we can see the result. We have segregation, even visually we can see we have segregation in OD and random diffusion. We don't have segregation in these two again. These two never give segregation. Okay, that's the conclusion. These two diffusion operators will never give segregation naturally. Okay. And in this case, we have segregation, but you see that the asymptotic value of infection fraction highest for these segregated guys. So segregation can make it worse even. So not necessarily is always good, right? Not always good. So we explore all possibilities for whether segregation can occur and whether that can lead to control of disease. Maybe yes, maybe not, right? Just combine different cases. Okay, so I think I skip this summary of these conclusions. Okay, thank you very much for your attention. And it's almost the last day. So thanks for your participation here. And if you have any questions, you can ask me. Again, the last and the most important thing, happy birthday, Professor Gail Workwitz. Yeah.
Postdoc